Hello everyone, in the series of basics of software defined radios and its practical applications, we were discussing the predistortion techniques, and among that today we will be discussing the topology for the digital predistortion techniques. So, these are the models which can be used to represent the inverse or the forward model for the power amplifier. The LUT is the one model which is representing the nonlinearity which is given by function f here. LUT is basically just the gain and phase response with respect to the input power. So, if we already know the input power, then we can arrange the inverse gain and phase also, and that information we can achieve from the actual I plus JQ complex baseband waveform which we provided by ourselves as a training sequence in the MATLAB, and the one which we captured from the vector signal analyzer again in the complex form. So, by using that LUT which we described in the last lecture, we can represent this nonlinear function. Now, we have earlier discussed the memory effect of power amplifier because of the temperature and the effects of elements such as capacitor and inductors. This power amplifier has memory effect. So, previously most of the researchers, they believed that these kind of memory effects are linear in nature. It means they fade with respect to time. So, if we look at the first structure which is called Wiener structure, Wiener is the name of researcher who proposed that we can use a FIR filter before this nonlinearity, and it should be able to give us the perfect model. The Hammerstein has proposed that we put a nonlinear function which is the LUT before a FIR filter, and that structure was called Hammerstein structure. Eventually, as the time progressed, many such structures and their variations came into picture. For example, Wiener Hammerstein structure is the one structure where we are using a FIR filter before the nonlinearity and one FIR filter after the nonlinearity, and this such a structure was called Wiener Hammerstein structure. As you can perceive by yourself, if we put this Hammerstein structure before the Wiener, then it will be called Hammerstein-Wiener model. So, basically it is just the placing of the FIR element and the nonlinear function in the system. Now, assumption was that the memory is linear. What does it mean? Our FIR filter this FIR filter actually is given as yn is a function of xn and its previous values. So, here we are assuming that output is a function of input and its previous values in a linear fashion. They are just multiplied with a constant and then they are being added together. So, when we have this assumption, we can use the FIR filter. So, in this case, in the Wiener structure, we are putting this FIR filter before this, and after whatever we are getting from the output of the FIR filter, we call it UN, as we can see from the structure here. So, this UN is something when this YN is applied to LUT. So, basically the LUT which was created using Pin versus gain and phase. Now, that Pin is being read by using this output from the FIR filter, and accordingly gain and phase is being applied to your digital predistortion system. So, it was Wiener system. First FIR and its output into the LUT, and LUT output will be the predistorted signal. In Hammerstein system, first of all, you will have your LUT. So, with respect to input x, you can read your value of gain and phase, So, you will have mean values, and according to x in you can read your gain and phase value. With that gain and phase value you can make your u value, which is un, which is again a complex number I dash plus j q dash based on this gain and phase applied with this input x n. And once you have this un, then this un is going through the FIR filter. So, your YPD predistorted output is actually a FIR function of un. Now, this YPD, it is compared with the required output of the predistorted function, and the coefficient of A's in this equation, they are adjusted to fit the model. In time there are some other models, some other variations. It was proposed that it is possible that they might not be completely linear kind of effect, but they can have some nonlinearity in the system. It is possible that x n is not simply related to x n minus 1 in a linear fashion, but x square may be. So, in that case some augmentation of such systems happen, and parallel Wiener-Hammerstein and you can say augmented Wiener-Hammerstein. Especially in the augmented Wiener-Hammerstein, you see x n is being multiplied with the absolute of its own. So, in this case, for this first loop, this x n which is being applied to LUT, parallel Wiener-Hammerstein method, this x n is what? X n is equal to function of FIR filter x in n plus the parallel branch. This branch is basically x in multiplied with absolute of x in and this is what being applied to function of FIR filter, right. So, this is the x n we are getting here, which will be applied to LUT. So, then output will be measured with respect to our ideal output of the inverse model or the forward model, and the coefficient of FIR will be tuned so that we have the best fitting there. So, in this case if you see here, it is not simply function of x in and its delayed version. One order has been increased. Now, it is using x square in a way, because what is x in n? It is basically absolute portion and phase of x in n in each case. So, if we see this one, it becomes actually, it is a function of a FIR function for sure, but apart from that it is also a function of x in squared. So, from here we can see it is using the second order. So, it is becoming more nonlinear here. So, it was found that this kind of complex structure were giving much better fitting performance. Now, this performances, they are measured in terms of performance of measurement. We have discussed earlier also. In band performance is measured in terms of normalized mean square error, which is given as 1 upon n y n minus y estimated n. So, it is mean square error, and when it is divided by its actual output at that time, then it is called normalized mean square error. So, what is the benefit here? That suppose the amplitude, the value of yn is very large, then it will lead to very large error values also, because if it is of the range 1000 and it is 998, then we are having of order 2, but if it is of order 1 and if it is 0.998, then it is of 0.002. It looks like it has smaller error, but the problem is not that it has smaller error. Thing is that its original amplitude was smaller, so we are getting the smaller error. So, it is not a fair comparison. So, that is why in the mean square error, which is given by only this equation, it is not sufficient. When we normalize it with the output value of the signal, actual signal, then it is normally normalized near the one value, and in that way for different kind of signals, different kind of amplitudes, we have a merit which we can use to compare different devices and different signals easily. So, normalized mean square error is the one which we use to check the in-band performance properly. Other performance measurement for the out of band performance, out of band performance can be given by ACPR, adjacent channel error power ratio. So, what is this ACPR? First of all, we do FFT or sorry DFT of our error. So, now this error is actually what? It is again yn minus y estimation. So, let us write it in that way, yn minus y estimated. So, we take FFT of these values and then we choose our frequency limitation. So, we choose our frequency in the adjacent band and we choose our frequency in the in band. So, when we compare these two matrices, it is using all the data in the time domain. In ACPR, we are choosing our data, we are again using error with respect to your original output which you are trying to model, but the difference is that we are doing this in the frequency domain. By choosing the adjacent channel, we are showing the error in the adjacent channel with respect to your actual signal FFT in the in band. So, for example, if this is the carrier frequency and this is system response simply, and we want to show the signal here. So, let us make it amplitude in fact, it will be better observed there. XF amplitude value. So, it looks something like that. Because of the power amplifier distortion, it used to be original signal, but now it will be this signal which is distorted and it is leaking into adjacent channels. Now, this is our carrier frequency and this is our in band area. So, we first of all plot the FFT which will look like that, and then we integrate our signal in band, the output signal. So, that value will be here, all these values, and then we will divide this value what we are getting here with respect to our error. Our error signal, for example, our model error is something like that. this is the error FFT. Then we take integration of this new area and this is the limitation of this adjacent. So, this is the area which we are integrating here. So, integration of this area with respect to integration of this area, this is what will give you ACPR, and it is out of band performance criteria. So, whenever you are comparing these models, you plot these two metric and you see if it is working well in the in band and it is working well in the out of band, and by checking that you can see which model is the best. So, here in this case we were finding that more complex models were giving more better NMSC and more better ACEPR. So, from that we got the motivation that maybe we should go to completely nonlinear models which have the nonlinear kernels. So, there came the models such as Volterra model and the feed forward neural network model. Now, neural network models are basically nonlinear in nature because they have neurons, and this function f is basically, this function f is basically nonlinear in nature. It is given by hyperbolic tangent function. Similarly, Volterra model, it is a summation of different multiplication of different input signal order terms, and they are also delayed by a particular amount, and it can go from infinite minus infinite to infinite. Means basically Volterra model says that we can multiply to any polynomial order and using any memory depth. Now, we can simplify actually this model. If you look at this Volterra model, if you want to open this term, let us put n equal to 1. If that happens, then what we will get? We will get n, it will just contain your first impulse function, impulse term h1, and it will contain your 1 delay. So, it is function of tau 1 only, 1 delay and x t minus tau. Similarly, it will be just with respect to d tau 1, it has only 1 delay term. So, if you go to h2, you can expand this expression and you can see that it will be having 2 delay terms, and it will be having 2 delay here also, x so it is function of 2 delay terms. And then it is integrating from minus infinite to infinite for both of them. So, if we keep increasing this term, it can go to infinite, but of course infinite cannot be processed. So, there are some simplified terms. One of them is called memory polynomial, and the simplified expression is given here. If you look at this term, it is basically representing the memory polynomial or the polynomial terms with different delay taps here. Okay. So, if you go to this one and try to simplify this, then instead of using different delay terms in the multiplication, what they are saying, because eventually your Hn will be summation of this one, h1n plus h2n and so on. So, they have simplified this term. Instead of using this one, this Hn is represented as memory polynomial, only diagonal terms are being taken. So, no multiplication of these two terms will be happening there. So, how it works basically, that yn becomes a function of xn and absolute value of x so j is equal to from 0 to n minus 1 or let us make it k minus 1, because n we are using for number of samples. This K is non-linearity order, and this M, let us take from 0 to capital M, this M we can call memory depth. So, generalized model is Volterra model, but Volterra model is very big model, it has to be condensed into a smaller model. So, this model came into picture, and it is a very popular model which is called memory polynomial model. Now, how it will work? When M is equal to 0, the output is only function of xn, because M is 0 here. So, it becomes only a polynomial series, right. So, we put a coefficient here which is a function of M comma j, and if we are tuning this coefficient, we are able to get our output easily from this expression. Once M equal to 1 comes into picture, then it will have x n minus 1 term also there. But you see, we are not multiplying n minus 1 and n minus 2 terms together, we are always using diagonal terms, we are always using similar terms. So, n minus 1 will be here, then also set n minus 1 will be here, and that term also will go from 0 to k minus 1. So, this is how we are explaining this term, that for m equal to 0, one polynomial branch, then m equal to 1 another polynomial branch, m equal to m another polynomial branch, and eventually they all are being added together. This nonlinearity is being applied to only absolute value, and the xn which is containing original phase is multiplied after this. So, same here, we are applying nonlinearity only in the absolute portion, and the main signal is being applied only once. So, the phase of the signal is not being multiplied nonlinearly in this case. So, this was the polynomial based model, and as you can see, many variations of this polynomial model you can do. For example, if you are allowing them to mix and match, and you make two streams here, and you say m it is m1 and m2, different values it can take, then in that case it is allowing it to mix and match. So, there are many models here which such as GMP, generalized memory polynomial, DDR model, dynamic deviation reduction based model, and they all are taking advantage of this Volterra series and making this memory polynomial a little bit more complicated, but to achieve better modeling performance. So, we are not going into all those models, because there are several in the literature, but the basis comes from the Volterra model and its deviations. So, these are kind of polynomial based models. Then recently neural network models, they are also much popular. This kind of models are kind of feed forward type of structures. So, as you can see here, they have nonlinear functions here, and they are connected with many connections here. Each connections have some weight. So, those weights are equivalent to this coefficient which we are using here. So, here we can tune this coefficient to fit our estimated output with the actual output. In neural networks, we can fit these weights in these connections, so that eventually this output is matching perfectly with the output of our system which is required. So, without going into details, they are subject of their own, but you can easily use them as a toolbox if you want to apply those to get some results. They are easily available in MATLAB, and there are toolboxes independently available in the literature also. So, basically once you have chosen which kind of structure you want to go with, maybe it kind of polynomial structure, or maybe neural network kind of structure, or you can even select some other kind of polynomial fittings, maybe spline fitting, and we have discussed the parametric models such as RAF model, Saleha model. They are also these kind of models which we can use for fitting. So, there are two factors in a model when you want to fit something. One is topology selection, which we have discussed, means if you are going for the polynomial model, what should be the nonlinearity order and what should be the memory depth. So, once you choose this topology, means choosing the nullity order and the memory depth, then you can go for the tuning of your actual coefficient, so that you can get your output easily. Similarly, neural network models also, you have to choose how many layers you want and how many neurons you want to keep in each layer. So, this is the part of the topology selections. Once you have chosen the topology, then second part is the filtering algorithm selection, which is the algorithm by which you are actually tuning your coefficient. So, in the next lecture we will be covering the filtering algorithm selection, and we will apply this particular algorithm to a particular topology, and we will see how it impacts our PA output linearization. Thank you.